All right, so what is a limit? A limit is the behavior of a function, f of x, aka our y values, as x approaches some value. Okay, so I have a couple things up here, and we'll go through a few ways to tell whether we have a limit or not. The biggest thing we're going to get out of today is determining if a limit exists or not. And then throughout the week, I will teach you algebraic strategies to find limits. And then next week, we'll look at obviously more limits. But this week, we're focusing on what is a limit, how can we tell graphically, and then we'll go through some algebraic strategies throughout the week. So, first of all, here is the function that we are talking about, all right? And we are evaluating the limit as x approaches 1 of our function, okay? So you'll see using this table of values, as our x values get closer to 1, what do our y values get close to? 3. So the limit as x approaches 1 is 3. If we look at this graphically, okay, I kind of like to think of like maybe a car or a train riding along the curve, okay? As we drive along the curve, okay, if we're coming from both sides, okay, as our x values approach 1, so as we drive on our curve close to 1, what y value are we approaching? 3. Okay, so the limit as x approaches 1 in this example is 3. As we get closer to 1, our y values get closer to 3. It does not matter if that is a whole or if it is an actual coordinate, okay? The whole point of a limit is we're getting infinitely, we're approaching that value. So if it's a whole there, it's okay. Okay, where is the whole? Okay, we're getting close to those y values of 3 because that's where the whole is. Okay. Okay, so let's look at this example. Okay, the limit as x approaches 2 of x squared minus 3x plus 2 all over x minus 2. So first of all, we're going to use a table. Notice how I have strategically picked x values that approach 2. See how we get closer and closer and closer and closer, really, really close to 2. So, part 1, please find me the y values for 1.75 and 1.9. Part 2, help me out with 1.99 and 1.999. Pod 3, 2.001 and 2.01. Pod 4, 2.1 and 2.25.
Alright, we'll do 1.75.
Feel free to break it up amongst yourselves. Okay.
1.75 squared minus
Okay, I'm going to kind of hop around a little bit. What is our function value at 1.75?
0.75.
What is our function value at 2.25?
26. Man, 2 is going to be a rapidly approaching.
I think
again.
I think
somewhere between.
Did anybody else do 2.25?
I did 2.1.
I got 1.2.
Thanks, man.
1.25 sounds a lot better.
We need to go.
Thank you. All right, 1.9.
I got 0.9.
2.1.
1.1. Oh, I see.
1.99. 2.01. Is that correct? Is that correct?
Yeah, that's right. I'm sad good. It just goes with the pattern.
We're not finding patterns.
1.999.
0.999. That was rude.
Pod 3, 2.001.
1.0.
All right. What y value are we approaching as our x gets extremely close to 2?
7.
Okay. Now, this whole setting at the table is not a strategy that you're going to use throughout the chapter. Okay, this is so you understand what's going on as we get close to an x value, what y value are we getting close to? Okay? So this is more of a teaching tool, so you see visually what's happening, okay? But let's go ahead and think about the graph. How do we graph a rational function?
Oh, you have to factor the top first.
We have to factor just in case, right? So this factors to
X minus 2, X minus 1.
So cancel.
Isn't there a whole?
yes. So what we're left with is x minus 1, which is a line. But what is happening?
There's a hole.
We have a hole.
There's a hole.
Okay. So we graph this. Let's see. Negative 1 is our y-intercept. We have a slope of 1. And we have a hole at x equals 2.
That's a 3.
Thanks. I was wondering what was. Okay, so here's our graph. Does everybody agree?
Yes.
Okay, so visually, okay, if we write along our function, and as our x values get close to 1, our y values approach this hole, which is at, okay, I said that backwards, didn't I? As our x values get close to 2, okay, we are approaching this hole, which has a y value of 1. So the limit as x approaches 1 is 2. Yes?
Why did you put x minus 1 in the second step?
Because we canceled this out, and that's all that we were left with is just that
Oh.
factor. Okay? Now, what if, in this same problem, I ask for the limit as x approaches 0?
Do you want us to figure it out, or can we use the graph?
You can use the graph. What y value are we approaching as x approaches 0? Negative 1. Okay, because that's what the coordinate is, right? Okay, so we can evaluate limits graphically whether we have a hole there or an actual coordinate. Okay, it goes the same way. All right. Okay, go ahead and write down this function. Okay, this is what we call a piecewise function, correct? Okay. Our function is 1 when x isn't 2, and it is 0 when x is 2. What does that mean? What is f of x equals 1? That is a horizontal line. So here is my horizontal line at 1, but not when x is 2, so we have a hole there. Our function is 0 only when x is 2, so we have a coordinate at 2, 0.
Just that one spot, just that.
Yeah. There's a hole in his bucket.
Hey.
Okay.
I laughed.
Thank you. All right, so what is the limit as x approaches 2 of this function?
No. Yes.
Let's drive our cars.
It's close to 0.
Wouldn't it be 2?
1.
0.
What's our function value? What function value, what y value are we approaching as we get close to 2? Has a height of 1.
Yeah.
Okay.
Because it's
But-
actually down there.
However, what if I asked you for f of 2? What is f of 2? 0. Okay, we'll talk about what that means later. Aaron?
I got it.
Okay.
I'm just gonna-
Now, biggest thing today are the 3 times that a limit does not exist. You must know these 3 times when a limit fails to exist. You might already remember the 3 times.
Those are my notes from last week.
So your notes from last year probably say something like this.
Yeah.
Okay? A limit does not exist if we approach different numbers from the right and the left. So as we come from the right, as we come from the left, if they're different, we do not have a limit.
Is that like with piecewise functions?
Yes, like what I have on the board. Let me draw that up here. Okay, so I don't even know what
Let's just say it's on the y-axis, so basically.
okay, so if this is like x is 2, the limit as x approaches 2 fails to exist because from the right and left we're approaching 2 different y values. Okay, so this is an example for 1. All right. Now, let's say that this is, I don't even know. Here at 3, okay, even though we have 2 pieces together, here at x equals 2, 3, 4, 5. Here at x equals 5, this limit would exist because we're still approaching the same value. It's coming from 2 different pieces, but it's still approaching the same value, and that's okay. All right. All right. Number 2, increases or decreases without bound as we get close to C. What would that look like?
Oh, they're doing
You're thinking of the next one.
inverse functions.
Okay.
Or
Okay, what do we have in those kind of functions? We have asymptotes. What happens at those vertical asymptotes?
rapidly approach that dimension.
One asymptote,
And
one
it
goes
continues to rise.
up, one goes down.
Not all the time.
Oh, right.
But if we were looking at this x is 2, if my graph was doing this, okay,
Graph there.
we are increasing without bound, decreasing without bound, okay, and so we say that the limit fails to exist.
Also not a function.
Correct. Yes.
So could you say that about the first example, the right side, how it keeps going up and up?
Well, we will talk about that next week when we talk about limits to infinity. We're not going to look, like how this goes up and up and up, that's talking about as x goes to infinity, what's happening to y.
Oh,
We're just going to stick with numeric values right now, okay? And then number 3, oscillates between 2 fixed values as x approaches c. You guys probably remember that picture, and I'll show you in a little bit, but we're oscillating and we get faster and faster and faster and faster, okay? If we have a limit that fails to exist, I want you to write D and E. Does not exist.
Done. Done.
Without the O.
Two.
All right, so let's look at some of these cases. Okay, this is a graph you need to know. Okay, you may remember this graph from last year. Okay, so first of all, as the limit as x approaches 0, absolute value of x over x does not exist, because as we approach 0 from the left, we're approaching -1, but as we approach from the right, we're approaching 1. So since those two aren't approaching the same y value, we say our limit does not exist. Okay, don't worry about that weird symbol right now.
Okay.
Okay? Now, why does this graph look the way that it does?
Because when we plug in a negative number for x, it looks like positive because of the absolute value.
Okay,
But the denominator value is still negative, so it's still a negative. So
let's think about what the absolute value means. Anytime our x is greater than 0, we're going to get, in this case, x over x, correct? Which is 1. Anytime x is less than 0, we're going to get x over negative x, which is -1. All right? So that's why the graph looks the way that it does. Why did I not say anything about 0?
Because it would be 0 over 0.
And that would be a sad day, right? We can't have 0 over 0. So notice how these are two open circles. Okay? You will see this graph even translated, like you may have the absolute value of x plus 5 over x plus 5. It's still going to work the same, except where would the break be here? The break would be at -5. Okay, so you'll see some examples like that, and you had some examples like that last year, potentially. Okay. Is everyone okay with that graph? Can we remember how to make that graph? Okay. Yep.
What if it's just like, can it ever be just x plus 5, or the absolute value of x plus 5 over x? Or is it not always going to be the same as the bottom, which one's actually fraction?
Let's see. We could have the absolute value of x plus 5 over x, but it would not look like this.
Okay.
Because you notice how every time we get, those are like, they're not common factors, but when we split it up, we have common factors and they reduce to just a value. If they weren't the same, we'd have what would we have?
The gap.
So for like these rules to apply, it's going to be the same on top and bottom.
Yeah, you may have like a 2 out here, and then it just, double in height, but you're always going to have that similar factor, yes. Yes.
I know you said not to worry about them, but now I'm curious about the else.
We'll talk about it in a little bit. Okay. Here's an example of unbounded behavior, and Jared, just for you, here's one that they do approach the same way.
Infinity, right?
Huh?
Could be infinity.
Well, right now we are going to say it does not exist.
Okay.
Okay? Later we'll talk about some infinities thrown in there, but as we approach 0, okay, from both sides, notice how we're approaching a vertical asymptote, so we're going to keep rising and rising and rising on both sides. Okay, this is unbounded behavior. The limit is failing to exist, so we're going to say it does not exist. And then especially like if we have, the typical reciprocal function where they're approaching the asymptote 2 different ways, not only is it unbounded, but then they go in 2 different directions. Okay, so you have a couple rules being broken there. All right, and then here is your oscillating behavior. This is the most famous one, the sine of 1 over x. You can see as we approach 0, we oscillate faster and faster between -1 and 1. The limit's not going to exist. Okay? This is one we're really only going to see graphically. We won't do anything algebraically with this. Okay?
So how do you ever know what one of those numbers is?
What?
Like, how do you know what 0 means in each of those numbers?
We can't plug in 0.
Oh, yeah.
So we don't
What
know.
about 1, 2,
If I want any of those values, we just plug them into the function. But since we have this reciprocal function inside, those numbers bounce faster and faster because these numbers get bigger and bigger. Just being curious.
Yeah, I don't like that.
Okay. Here I have a graph. I would like you to evaluate these 4 things. So first, I would like you to do it on your own.
The graph on the right, I'm not seeing the graph on the left.
What are you trying to the right of what?
That's all right. Final graph.
Is there not some
Yeah,
Oh,
it's
you mean-
asymptotic 0 for that graph. Okay.
Better.
Yeah.
Okay. Okay. Someone from pod 1, what is the limit as x approaches 0? Does not exist. Do you agree? Okay. Whether this is unbounded or not, okay, we're approaching 2 from 2 different, the left and the right aren't meeting up, right? We have a break in the graph right there. So the left and the right are approaching 2 different things. Our limit fails to exist. Okay. Someone from pod 2, what is the limit as x approaches 3? $3.1. We can't tell exactly. We'll say it goes to 3. Okay. Any questions?
I don't think so.
Okay, you can fix it. Okay, everyone okay with 3? We're gonna call it 3. Is that okay? Okay. Pod 3, f of 0.
Undefined?
I disagree. It is -2. Okay, this is the function value at 0. I have a coordinate at 0, -2. Okay. Anytime you're just asked for the function value, we're looking for the coordinate. Okay. And the limit as x approaches -2. Someone from pod 4.
It's like,
1.5. Somewhere around there. Beautiful. Questions on any of those? Yes.
How did the first one not exist?
Because as we go from the left and the right, we're approaching 2 different values. Okay. I want you to think about this graph. For what values does the limit fail to exist here? Don't yell it out. Look at the graph and think about it. our two areas of concern be? At -4 and 2. So, who says the limit as x approaches -4 does not exist? Good, you would be correct, because as we approach from the left and right, we approach two different y values, so it does not exist. Who says the limit does not exist as we approach 2? Good. What is the limit as x approaches 2? It's not 1? It's 2. Yes, Aaron?
I was gonna answer.
Oh, okay. Thank you. All right.
When have you ever raised it?
What would the answer? When would I have an answer of 1? If it was just f of 2. Very good. Okay. So what was that funky symbol?
Alpha.
This ends. It was delta. This ends our notes. Okay. What I'm going to talk about is something that you won't see unless you take theoretical mathematics. But some of you may go on to take theoretical mathematics. What do I mean by theoretical mathematics?
Well, I use that,
Okay.
so I won't need to.
So, like I took theoretical mathematics to become a math teacher. Okay, if you major in math, you will take theoretical mathematics. Okay. Now, if you are an engineer, you're gonna stick more with the it's all math. Okay, the computational math. All right, but you'll have some theoretical like physics classes. Anyway, so the formal definition of a limit. F of x becomes arbitrarily close to L. Okay? Epsilon is a really, really small positive number. Really, really small. Okay? And f of x is going to become arbitrarily close. So what does that mean? That means our function value lies in this really, really small interval. Okay? We're getting really close. So it's lying in this itty bitty bitty interval that we're approaching. Okay? Which means this. The difference in our function value in L is smaller than this really, really, really tiny number. Okay? X approaches C. What does that mean? Okay, you guys saw this symbol in that picture, right? Okay. We're going to have a positive number, and we have the same kind of thing. X lies in this really, really tiny interval. Okay. In other words, this. Okay, so basically what's happening is we're zooming in into this really itty bitty bitty area. And this is what it looks like mathematically. Yes?
We just talked about the tree, and she said it means partially. That could be the same thing. Or could it mean different things?
It can mean different things. Mm-hmm.
So we can use a triangle and look at those.
Yeah. Okay. So here is our statement of a limit. The limit as f of x approaches L means that for each epsilon, there is a delta such that this. So that's all the symbols that I just got done talking about, right? So as you zoom in, our limit is somewhere in that really zoomed in magnified area. Okay? I'm not going to make you do anything with this, but if you get into theoretical mathematics, like you're going to actually have to use this to prove limits.
I understand the zero.
Here's your homework.
I think I got the whole echelon part.
It can be a
Not here.
It's